Hey there, chemists. In this crash course, we are going to look at what you need to know for gases and behaviors of gases. There's a lot of equations you probably learned related to gases, namely the ideal gas law, pressure times volume is equal to the moles of a gas times the constant times temperature. Your constant and this equation are on your reference table, but it's always faster if you just know it. R is 0.08. 206, and the units in that constant remind you of every unit you need in order to use the ideal gas law, liter atmosphere per mole per Kelvin. And there's a very useful relationship called STP, meaning standard temperature and pressure. That is 1 atmosphere, 273 Kelvin, and the molar ratio, what's called the molar volume, of 22.4 liters per mole. That is always true. And we'll use some combinations of these numbers to help us figure out some useful mathematical things where you don't even necessarily need a calculator. So within this equation are lots of properties of gases. For example, if we go to a little particle simulator, let's take a look at just a random sampling of gases. Here they are occupying this space. If I compress them to a smaller volume, the pressure will increase. Pressure and volume are inversely related. Likewise, if I expand the volume, the pressure decreases. Pressure is the collisions of the particles against the walls of the container, which in this case is just the rectangle of the screen. Temperature is related to pressure. If I heat things up, there are more collisions with the walls. So as temperature increases, pressure increases. If I cool them down, the pressure decreases because there's fewer collisions with the walls. You can tell because the particles just start to move more slowly. And all those relationships are inside this equation right here. There's the inverse relationship between pressure and volume. As one goes up, the other goes down. There's the direct relationship between pressure and temperature. As one goes up, the other goes up. Likewise, there's a direct relationship between volume and temperature, volume and moles, etc. All those relations are in that one equation. Now, pressure is the newest thing that we're talking about when we come to gases. And when you think about the pressure of a gas, it's really just analogous to an amount. Saying I have 3 atmospheres of hydrogen is analogous to someone else saying I have some number of moles of hydrogen or some number of grams of hydrogen. It's just another way of saying an amount of that gas. Pressures are additive, so the total pressure of a mixture is simply the sum of all the partial pressures. This is called Dalton's law. So 2 atmospheres plus 3 atmospheres plus 4 atmospheres would add up to give me 9 atmospheres of a gas, provided that the volume and temperature are kept the same. But that's useful if you're doing just mixing of gases or thinking about how they react in multiple ratios for chemical reactions. Species react in mole to mole ratios, but they also react in pressure to pressure ratios for gases or volume to volume ratios, provided other things are held the same. Thirdly, what about the speeds of gases? We actually saw in that animation how gas speed is related to temperature. It's actually related to 2 things. The speed of a gas is related to how hot it is and how heavy it is. So hotter and smaller equals faster. Conceptually, that's really all you need to know right there. If you have a hot sample of gas and there's small atoms or molecules, they will move faster. And then the opposite is true. The heavier they get, the slower they get. The colder they get, the slower they get. There's also a common graph you might see that looks like a distribution of the relative number of molecules versus speed. And if I look at, let's say, some cold temperature and compare it with a hot temperature that might look like that, the area underneath these curves indicates all the molecules that are in a distribution of speeds. They're not all going the same speed, but there's a relative average. And then at higher temperatures, you get a wider distribution of speeds and just greater speeds, as opposed to cooling a gas down. They're all lower inside this curve. They're to the left on the x-axis, and there's a narrower distribution. Notice the area of the curve is roughly the same because it's the area that matters. You won't have the same height. We'll see that in a couple of sample problems in a moment. Lastly, let's just talk about real gases as opposed to ideal gases. So when we think about a sample of an ideal gas is made out of infinitesimally small particles that don't interact with each other. They occupy all the volume that they're contained in. Gases fill up the space, whether they're alone or with another gas. They always occupy everything. And then they collide off each other elastically. Sorry, those are ideal gases. These are ideal gases. Let me label this. Now, how is this different than real gases? Well, real gases actually have measurable volume to their particles. So they actually occupy space. This is quite an exaggeration, but you can imagine a mixture of some gases that are actually occupying space, and they interact with each other. They have attractive forces. So large molecules behave more real than ideal. The ideal gas law, all the things that we've been using to calculate things related to gases, really only work for small, non-polar gaseous things. And you want to remember that the gases always behave most ideally when things are hot, at high temperatures, and low pressures. That's your best ideal case. You might be asked about deviations from ideal gas laws. So the deviation graph looks something like this. We would normally look at, let's say, a pressure versus volume, which is an inverse relationship, and it looks something like that for an ideal scenario. But a real case would look something like that. And what this curve shows is that as you increase the pressure of a sample of gas, the measured volume is not going to be as small as you think. It's going to actually be bigger. So the volume of a real gas is greater up here. And that makes sense because as you compress something in a smaller space, the volume of these particles actually occupies space. So a measured volume would be greater than what it is under the ideal law calculation. And then likewise, you get to this other section of the graph. If you all of a sudden get really big volumes and you expand it out, well, then the interactive forces are more significant, and the real pressure that's measured is actually less. It's lower. And that's because as you have lower pressures and greater volumes, you see a predicted pressure of some ideal calculation, and the actual pressure is smaller because the particles are actually interacting with each other. They stick together and they don't hit the walls of the container. Pressure is due to particles hitting the walls of the container. That's what pressure is. But if these particles are sticking together with various adhesive forces and intermolecular forces, your pressure will simply be lower. Okay, that's a rundown of some of the things that will be expected to use. Let's look at some sample questions. So, starting with some multiple choice. A 2-liter container at STP will hold about 4 grams of which gas? So to identify a gas from its formula, we're really trying to find out its molar mass. You know, what's the molar mass of the gas, which is how many grams per mole. Now STP, remember, is 22.4 liters per mole normally, but we're looking at 2 liters of a gas, and so we can't actually use that. So that is not helpful at this time. But it is 1 atm and 273 Kelvin. So I want to know the molar mass of a gas, and the ideal gas law, PV equals nRT. You can replace N in the ideal gas law with mass over molar mass, and then when you solve for the molar mass, you get mass times R times temperature over pressure times volume. So the molar mass of a gas is based on how hot it is, the pressure, its volume, and how much of it you have. We have 4 grams times 0.08206 R value times standard temperature 273 all over the pressure of 1 and a volume of 2. Now, multiple choice questions are typically done without a calculator, and you look at this and you go, how the heck do I do this without a calculator? Aha, there's a good trick. The R value times the standard temperature, that is the molar volume. That's 22.4. That's where that comes from. That would be if we had if you use the ideal gas law, P equals nRT, that's when you have 1 mole. So really what I have to do is 4 divided by 2, and then times 22.4. Well, 4 divided by 2 is 2. So 22.4 times 2 is about 44.8. No calculator needed. And scanning the molar masses, carbon dioxide weighs 44 grams per mole. So choice C is the correct answer. You could prove it with a calculator. Go through, check all these other molar masses, they wouldn't be correct. Sulfur dioxide is about 64, N2 is 28, ammonia is 17, C4H8, that'd be 48 plus 8, about 56. So CO2 is by far the best answer when you're comparing those molar masses. All right, next. The graph below shows a distribution of speeds for oxygen at some temperature. Which one shows the distribution at a higher temperature? Well, if it's hotter, it's going to have a wider distribution, higher speeds, but the same area, so a lower peak. So we're looking for a dashed line. That looks like that curve I just drew, and there we go. 5 seconds, we found the answer. Next, below shows 2 rigid 5-liter containers, each with a sample of gas at the same temperature, but different pressures. Okay, so I can see that 0.8 and 1.0. They're combined into a single 5-liter vessel. So this is just put in this container, and the nitrogen is put into the same container. What's the total pressure after being combined, assuming ideal behaviors? Now, this is a great reminder of how the fact that gases are selfish. They occupy the whole volume in which they are contained, no matter who else is there. So the pressure of the oxygen in the new container is still 0.8 atmospheres. And the pressure of the nitrogen in the new container is still 1.0. We just have to add them together. The total pressure is the sum of the two, but the partial pressures are actually the same because the volume of the container is the same, the amount of particles is the same, and the temperature is the same. Then we just add the pressures. So it can be determined. It's not more than or less than 1.8. It is exactly 1.8 because it only depends on the total amount of gas when volume and temperature are held the same. All right, one more multiple choice. The graph below shows how a particular real gas deviates. This is the graph we just looked at, which is the most likely identity of the gas, and gives a reason for this. So we already explained this graph. This is a good reminder of how those two deviations of real gases usually cancel each other out. That's why the curves sort of cross each other. Turns out the deviation is much more noticeable at higher pressures, as I think you can tell. That makes sense. Gases want to be in an expanded low pressure state. High pressure is when things don't look like gases anymore. You start to liquefy them. So you're going to get a larger volume than expected. So what's the best reason for that? We must have a big molecule. Big molecules. Bigger molecules don't behave ideally because they stick to each other and they have actual volume. So of the 4 gases in the choices, looks like the one that has the biggest volume is the one they actually tell me. Choice D, sulfur dioxide. I can look at the rest. The small mass of hydrogen would actually make it behave kind of ideally. The triple bond of nitrogen has nothing to do with its ideal behavior. Likewise, the filled valent shells of neon don't affect its ideal behavior either. It's just the types of intermolecular forces and how big the molecule actually is. Okay, I actually have a few more multiple choice. So the diagram below shows speeds of particles with the arrows. They do this a lot to simulate things. Which best shows a sample of gas at a fixed temperature? Looking at the two diagrams, it looks like diagram 1 has arrows that are all the same. Diagram 2 has arrows that are slightly different, and that is a better picture because there's always a distribution of speeds. At the same temperature, you have a given kinetic energy. The average kinetic energy is based on temperature. It's actually 3/2 the constant times temperature. because kinetic energy is what temperature measures on a macroscopic scale, but there's a distribution of speeds. They're actually not all the same. So the better diagram would be 2, which means A and B are out. And they say they have a variety of different speeds, so D is the best choice. Next, at 10 Celsius, 20 grams of oxygen in 7 liters has a pressure of 2.1 atm. What's the new pressure if the gas is heated to 40 and all other factors are held constant? So we are looking at temperature changes and wondering what the new pressure is. So the ideal gas law, which is actually an extension of the combined gas law, P1 V1 over T1, is P2 V2 over T2. The volume is the same, so I actually get rid of those volumes. And then we can substitute our initial pressure of 2.1, our initial temperature of, it's not 10, it's 283, because we have to put it in Kelvin. And our new temperature is 30 more than that, which would be 313. So P2 would be the original 2.1 times 313 divided by 283. It's not doubled, but it's certainly greater than the original. That makes sense. You heat it up, it heats up. So what's the new pressure? It's got to be more than 2.1, but not a whole lot more. So I'm looking at choice B, and there's the correct factor, 313 over 283. Lastly, a vessel contains a mixture of gases. The mass of each gas is used to make, the mass of each one used to make it is known. What do you need to get the mole fraction of each gas? So we know the masses, but we need mole fraction. We need the molar mass of each gas. It must be A. The density doesn't give you mole fraction. Total pressure doesn't do it. We need to convert it into moles. So mole fraction is simply, if you have the mole fraction of one part, it's the moles of that substance divided by the total moles of everything. So if it's, let's say, 2 gases, that's it. It's a unitless value. And remember, moles is mass over molar mass. So what we're missing is the molar mass of each gas. Okay, let's wrap up by just looking at one true response question. A student performs the reaction of solid magnesium with aqueous hydrochloric acid and collects gas by water displacement. This is a common thing that many of you should have done, where you collect some gas above a container of water. That means what's in here is actually the gas plus the water vapor. That's just always true whenever you do something above water. So you have a mixture of gases and the pressures are additive. What's the net ionic reaction? Well, we have solid magnesium plus hydrochloric acid. This will do a single replacement reaction. Metals plus acid make hydrogen gas. Every chemist should just know that. And then you would make the salt, magnesium chloride. However, that's not the net ionic. Chloride will be a spectator, so I'm going to get rid of the chloride in the beginning and put an H+. And I'm going to get rid of these 2 chlorides over here and put a 2+. That means I need a 2 in front of my H+ in the reactants. There's your net ionic reaction. B, they run it at 298 Kelvin, 765 torr, 45.6 mils are collected. The vapor pressure of water, meaning the partial pressure of water, is 24. What's the pressure of just the hydrogen? Well, the pressure of just the hydrogen would be the total minus the water. This is Dalton's law. Partial pressures are additive to give a total, so I subtract the water from the total. 765 minus 24, and you get 741 torr. And then how many moles of hydrogen? Rearrange the ideal gas law. N is PV over RT. Pressure is 741, got to convert it into ATMs, so divide by 760. V is 45.6, got to convert it into liters, so divide by 1,000. R, it's faster if you know it, 0.08206. T, 298 Kelvin, already in Kelvin. So my units are good. Simply need to convert everything and plug it into my calculator here, divided by 0.08206 and 298. And looks like they're using almost exclusively 3 sig figs for things. Not that vapor pressure, but once I subtract it, I still get 3. So I'm going to round this to 3 sig figs, and I get 0.00182 moles of H2. And there we go. So that's a good review of gases. Thanks for watching.